In our previous video, I have briefly introduced logistic regression. But before we talk about logistic regression, we have to talk about linear regression. First off, what is regression? It's a method to draw a trend by finding a mathematical relationship between a dependent factor and one or many independent factors. Like salary would be a dependent factor that's dependent on an independent factor like experience. Let's take that very example. Here, I have data of employees with their experiences spread across 0 to 10 years and their salaries ranging from 0 to 120,000 per month. Now, based on the data, if you squint your eyes, or even close your eyes all the way for that matter, you can clearly say salary rises as the experience grows. So I could say it's an upward line. But is that good enough? Definitely not. I should be able to tell as precisely as possible how much should my y grow with respect to my x. In other words, at what multiple? That's it. Y equals mx. What multiple of x should be my y? But remember, there's also a starting point for our salary, meaning a person with zero experience can't be paid 0 rupees. And that's why we add the base, or in mathematical terms, a y-intercept. So my y, which is my estimation of that salary, can be given as mx plus b. I'll just call it y equals ax plus b. Great. Now we understand what this pseudo line would give our expected salaries to be. But remember, we still don't have the actual line. These values a and b are still nothing to us. All we have is a bunch of data. But lucky for us, we can draw out this line by working out what we actually expect from this line. We expect this line to be as less erroneous as possible. That is, when I look at it as a whole, the sum of the differences between my estimated salary at a given point and the actual salary at that point to be as less as possible. But there's a problem here. Some of these estimated values at a given experience level could be higher than the actual salary, and some of these expectations can be lower. And if that's the case, a higher positive error would balance out a higher negative error, bringing it close to zero even if the line brings such high errors. To avoid that, we can either take absolute values or the squares of it. We'll take squares and you'll know why in a couple of minutes. So now I want the sum of squares of differences between these estimated salaries at some point of experience and actual salary at that point of experience to be minimum. So my squared error can be given as summation of estimated salary at I minus actual salary at I whole squared. But we know estimated salary at I can be written as AXI plus B. So I'll rewrite my squared error as summation of AXI plus B minus YI whole square. So now I want this whole thing to be as less as possible. In other words, I want my squared error to be minimum. You might remember from calculus that in order to find minima or maxima, we find the first order derivative of that function and see where that will be zero. I can quickly give you a visualization of how this works. Here you can see a graph with some highs and some lows and some points which are neither highs nor lows. But if you observe, there are some points of this graph which seem to look stagnated, which means the values of y don't change at some points with respect to x. Now these points are this, this, and this. So now this point is called a maxima, this point is a minima, and this point is a saddle point. All these points will give the derivative as zero because there's no change. Let's just forget the saddle point, which is neither minima nor maxima, for a second. Now, since these both are giving me as derivative 0, how would I say that which is minima and which is maxima? That's simple. If this graph is going downwards after this point, in other words, my second order derivative is negative, I can say that this point is maximum. And if this point takes the graph upwards, in other words, if the second order derivative of this point is positive, I can say this is minimum. I can assure you that both of these values that we are going to work out with are going to give the second order derivative as positive. So both these points are going to be minima. Well, now I want the derivative of the squared error to be 0 so that I can find the values of a and b, which will give me the minimum squared error. Now since we have two variables here, I'll have to work with the partial derivatives. So I'll differentiate this equation with respect to b once and with respect to a once. First, dou over dou b of this function equals 0. I can take the derivative inside the summation. That will make summation of dou over dou b of this function squared. We know the derivative of function squared will be 2 into that function, and do not forget the chain rule, we have to differentiate that function again. So summation of 2 into that function into dou over dou b of that function. This whole thing will be equal to 1 because remember we are only differentiating with respect to b. That will give us 2 multiplied by the summation of axi plus b minus yi equals 0. And if we solve this, we'll get the value b equals summation of yi minus a into summation of xi over n. Well, this is good. This is what we want. But then there's a. We don't know the value of a. Let's work that. Let's do the partial derivative with respect to a of this function. Again, I'll take the derivative inside the summation. So summation of dou over dou a of this function squared equals 0. So again, a function squared will give me 2 into that function, and again the partial derivative of that function. So summation of 2 into axi plus b minus yi, and remember this whole function, its derivative with respect to a will give us xi. Now that will become summation of 2xi multiplied by axi plus b minus yi equals 0. Well, in this equation we can substitute b, and once we substitute that and work our values, we'll get the value of a to be n into summation of xi yi minus summation of xi into summation of yi over n into summation of xi square minus summation of xi whole square. Great, now we got the values of a and b. And now these values of a and b are in the terms of x and y, which means these are in the terms of the bunch of data that we have. Now all we have to do is plug those values in these and get the values of a and b, which will give us this beautiful line that will fit this data.